Imagine standing inside a metallic cathedral, deafened by a rhythmic mechanical thunder. Pistons over 3 feet wide plunge up and down with unstoppable force. A single unit of this slow-speed, two-stroke diesel engine produces up to 40 megawatts of power. This is the engine room of a modern cargo ship, the beating heart of global trade. For a century, iron ships relied on a much more brutal source of power. Steam engines were dangerously hot and required a massive workforce, a black gang of stokers and coal trimmers, for the constant feeding of roaring furnaces. Those steam boilers demanded a heavy, complex network of pipes and condensers. Combined with massive coal bunkers, the propulsion system devoured the ship's internal capacity. As global trade demanded more speed and higher capacity, the sheer bulk and weight of these steam systems meant the technology had reached its physical limit. To meet growing global demand, shipbuilders had to engineer a lighter, leaner alternative to the steam engine. The first half of the solution lay in the material of the hull itself. Shipyards replaced heavy iron with steel, an exceptionally strong, watertight, and highly weldable iron-carbon alloy. Paired with that lighter hull was a different way to generate power, patented in 1892 by Rudolf Diesel. Instead of an external boiler, a diesel engine uses internal combustion. It compresses air so intensely that heat triggers spontaneous combustion when liquid fuel is introduced. Because it's liquid, fuel flows through pipes instead of being shoveled, slashing crew requirements and operational costs. By standardizing around this slow-speed, two-stroke diesel engine, the shipping industry eliminated entire layers of mechanical complexity and achieved levels of thermal efficiency impossible under steam. When the ocean-going diesel revolution arrived in 1912 with the launch of the MS Selandia, it confused onlookers. The ship lacked the billowing traditional smokestacks associated with industrial power, leading some harbor pilots to call her a phantom ship. But the numbers were impossible to argue with. On her maiden voyage from Copenhagen to Bangkok, the Selandia consumed only 800 tons of fuel, a 40% cost advantage over comparable steamships. That economic power allowed owners to scale up. Maritime trade fragmented into specialized steel workhorses, like massive tankers carrying liquid energy across entire oceans. The diesel engines solved the propulsion bottleneck on the water, but as these ships grew, they triggered a new bottleneck the moment they reached the dock. A single large cargo vessel could carry thousands of individual items, bags of coffee, crates of machinery, barrels of chemicals. Unloading each one by hand took weeks, negating the speed and capacity of the ship. The solution to this port delay was a logistical breakthrough called containerization. Instead of loose items, freight transport moved into standardized steel boxes. These identical units could transfer seamlessly from ships to trains and trucks, without their contents ever being handled individually. Using massive gantry cranes to hoist boxes into purpose-built cell guides, a modern terminal can load or unload a giant vessel in under 24 hours. The combination of the diesel engine and the standardized box created an invisible conveyor belt for globalization. Today, 90% of the world's trade by value moves through this system. This global mobility has come at a compounding environmental cost, one that rises directly from the funnel of every ship. To run these colossal engines cheaply, the industry relies on heavy fuel oil. It is a thick, dark residual product left over after crude oil refining, a residual sludge packed with sulfur and other impurities. Burning this fuel releases massive volumes of carbon dioxide, nitrogen oxides, and sulfur oxides into the atmosphere, pollutants linked to ocean acidification and respiratory disease in coastal populations. Because these vessels operate far offshore in international waters, their emissions, which account for roughly 3% of global greenhouse gases, remained largely unregulated for decades. By optimizing for economic scale, the industry built an incredible machine that is now causing significant atmospheric damage. The International Maritime Organization has responded with tighter regulation, mandating strict caps on sulfur content to curb this pollution. While some owners installed exhaust gas scrubbers, these technologies only trim the problem at the margins. The IMO's target to reduce total greenhouse gas emissions by 70% by 2050 requires a complete reinvention of the fleet. The heavy, oil-burning diesel engine is now facing its own limits. Engineers are already deploying the next generation of power: cleaner-burning methanol fuels, zero-carbon liquid ammonia, advanced hydrogen fuel cells, and even high-tech wind-assist sails. Just as shipbuilders engineered their way out of the limits of steam, they must now engineer a path out of the carbon bottleneck. The next great voyage has already begun.